Okay, good afternoon, everybody, or good morning if you are on a time zone where it's morning, or good evening if you are in the evening. So this is the latest of the Machine Learning for Science seminar, and today is a big pleasure for me to introduce you to Juan Carrasquilla, who is at the moment is a faculty both in University of Waterloo and at the Vector Institute in Toronto. So for those of you who don't know Juan, he graduated from CISA in Trieste, and then took up a number of postdoc positions in the US and then in Canada, where then he has established his group in Waterloo. I think Juan and I met some time ago in Trieste, and when he was presenting some talk on, I believe, somehow recognizing phase transition particularly in the easy model, and I thought was a very, very creative way to use machine learning, and then that's why we decided to have him here. So I guess without any further ado, I'll just would like to give you the stage, please.
Yeah, thank you so much, Stefano, and thanks for this kind invitation. I'm excited to be here, and I hope everybody is healthy and staying safe. So I'm going to tell you about general models and with probability in general. Usual in that usually quantum states are represented using density matrices and wave functions, and but this is kind of like a little bit different in that we're, instead of using those objects, we're going to be using probability distributions, okay? And that's basically the topic of what I'm going to tell you. And these are my collaborators, so Diluo, Felipe Perez, Maxim Volkovs, Leandro and Brian Clark. And so let me start by reminding you of a 1981 paper by Feynman. It's called Simulating Physics with Computers. And this was not a paper on its own. It's more like a keynote speech he gave at Caltech in okay. And this paper is kind of like foundational for the quantum computing field. Because this is the paper where he introduced the idea of quantum computations and so on that motivated and shaped the field of quantum computing, which we still hopes to revolutionize computation through the exploitation of quantum mechanical effects. So this is a very interesting paper. It's like a transcription of one of his talks, and so I really like it. And I guess I was motivated about this paper because of the following. So there's a section, it's section 5 here, where he asked the question, can quantum systems be probabilistically simulated by a classical computer? And so he explores this question in detail, and he basically comes up with an answer. The answer is no, right? Like that we cannot simulate quantum system with probability, and this is basically still true today. And it is indeed fundamentally linked to the notion of quantum speed up in quantum computing. And the answer, I mean, it remains true, is still no, but I guess what I wanted to ask is, what I wanted to phrase was like, we can do the simulations of quantum states and real-time dynamics of quantum many-body systems using probability if we want to do it exactly, right? Like, so that's the question he asked. So can we do it exactly? But the question I want to ask today, or that we've been asking in the past few months, is can we do it in a variational way? And this is where we enter, or we use generative models. So this is basically the topic of the talk, right? Like, can we use generative models and some variational principle to simulate quantum circuits or quantum dynamics, which is a very challenging problem in general for like quantum many-body physics. So before I go on with the details, let me just give you an example of what these generative models do, right? Like, as I'm mentioning, and I'm going to be using them, but I haven't told you how people use generative models. So this is an example of text generation using neural language models. So basically, what you do is you prompt the system with a handwritten text that you create. So here in this example, I have this prompt. So in a shocking finding, scientists discover a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains, and so on. There's some like some phrase, right? Like, and that's your input, and this neural language models produce an outcome, right? Like, and the outcome is what's written here in the model completion, which is machine written, okay? And then what you see is like a very coherent page of text, roughly over a page, and it looks really good, right? Like, so for instance, the scientists named the population after their distinctive horn of its unicorn, right? Like, so it's still a little crazy, but it's pretty coherent. It mentions even Dr. Jorge Perez, which is a name that is very common in South America, and because the text is, I mean, the prompt contains the word "ants," which is has a large fraction of it is, or almost all of it is in South America, and so everything is very very coherent and very interesting. And so which I mean my point is here is to demonstrate that this neural language models are very powerful, and that's what we're going to be using here, right? Like, so with this example, so here's another one which is I found really funny. This is from a tweet by Chris Ferry, which is in quantum information physicist. So basically the prompt is this input here. So the prompt is just this word, right? Using quantum computers, and then this model completes the text, and it just writes something very coherent, right? Like, quantum computers to make sense of the vast amounts of data floating around out there in the form of tiny bits of energy called qubits. So it's all related, but it seems to me that AI knows too much, since this is before like the Google supremacy experiment. So they say we've seen from Google's recent experiment with a piece of paper containing information, and even quantum computing will only be used to manipulate information and so on. So it's all very, very interesting, and it seems like this transformers, like these models used for generation, are really powerful. And so that's what we want to exploit. So what are these models capturing or modeling? So what they do is they basically model this probability, this conditional distribution of some output text conditioned on some input text, which is this, for instance, using quantum computers, right? And as you see, like, there's this probability distribution of the output condition on the input, and then basically what you do is you sample this probability of output text, and then you find this sort of like coherent text, which to me seems very surprising and very powerful, right? Like, so, and these techniques are based basically on powerful neural probabilistic language models, and this is very surprising to me. And so what I was wondering is, can we use this power for us to simulate quantum computation or quantum circuits or quantum dynamics? So that's what we're trying to do. The other surprising thing is that these models are very powerful, and they're capable of reproducing correctly the strong correlations present in language, which are typically power law. And this also shows up in music and in natural images and so on. We see a lot of like strong correlations in the form of power laws, and those models seem to be really good at capturing those. So what are these neural language models? They're neural networks which model language, right? And what are neural networks? As you probably all know, is they're just powerful universal function approximators that can in principle compute any function if you put enough like parameters, right? So it is, like, to me, it is natural to ask whether or not these models can represent complex quantum systems. So that's what we're going to explore here. And why? Because there's some commonalities between the quantum states and quantum systems and this neural machine translation models. So one of them is the dimensionality, which I'm going to discuss right here, which is just the fact that the size of the Hilbert space of a quantum many-body system grows exponentially with the size of the system. So if you have, say, n qubits or n spin 1/2 particles, then the wave function lives in a Hilbert space, the size of which is like exponentially big. So it's order it's actually indeed 2 to the n component vector. So this is growing exponentially fast, and it's so bad that even using today's best supercomputers, you can solve the wave equation exactly only for about 45 spins. So which is tiny, and the size of the Hilbert space is basically 3.5 times 10 to the 13, which is just really large. And that's the dimensionality that we use to handle in quantum many-body physics. But if you go and see language translation models and like this neural network that people use for this type of systems, they're also very high dimensional, right? So for example, I have here one example of a paper called Attention is All You Need. It's a language translation paper, if I remember, or a language modeling paper. And here the count is a little bit different. So what you do is like you replace the number of states. Here in the spin case, we have like, I don't know, up and down, so that's 2. And you replace that by the vocabulary size. Okay, and so here I'm using 8,000 different words, which is usually the number of words you need to be able to understand pretty well. Like I think it was an article on the BBC, for instance. So 8,000 words in English, and then you have some length of a sentence, and in the paper they use sentences of up to 100 words, and so that comes up to very large dimension over which you define this neural machine translation model. So it's 8,000 to 100, which is this really, really big number, which means that these distributions are as high dimensional as many-body systems. Okay, so and so that's, if you want, one commonality. The other one is perhaps most important is both quantum states, natural images, and natural language are somehow physical, right? Like, so meaning that the amount of information stored in a quantum state or in a language model or in a computer vision model is typically smaller than this maximum capacity, right? Like, so we don't anticipate that like a physical quantum state has an amount of information which is 2 to the n, but it's going to be much lower. And that's also true for natural images and natural languages, right? They all arise from physical processes anyway. So the anticipation is that we don't need this high-dimensional vectors to do a good description of the physics that we see and of the languages and so on. And this is what we exploit, for instance, when we do quantum Monte Carlo simulation and other numerical methods based, for instance, on tensor networks. We exploit this fact. And quantum Monte Carlo, what we do is we exploit the fact that for you to get expectation value of, say, local observables and other quantities, all you have to do is do a stochastic exploration of this like extremely high dimensional space, and that's usually enough for you to get these calculations that are really useful for us to understand quantum many-body physics. And what we do in tensor networks is we take into account the low entanglement structure of the physical quantum states to write down approximations of complicated exponentially big quantum states in terms of, say, products of simplified tensors, right? So we're like when we solve these problems in quantum many-body physics, it almost seems like a miracle, but what we do is just exploit the structure of the physics that we are trying to describe. And that's what people do in machine learning as well, right? Like, so it turns out that both quantum physics and machine learning problems had a lot of structure, that symmetry that we can exploit. And even some of that structure is shared among the models. And we have examples of that, right? Like, so for instance, in here we have this Hilbert space, and we know already that some neural network can represent some quantum states that are in common with, say, tensor networks. But we also know that some quantum state that you can represent with neural networks, you cannot represent with tensor networks, and vice versa. Okay, so that's if you want the message, is that there's a common structure because of the way the correlations of, say, natural images and natural languages behave, that induce like this type of like common structure between what models in machine learning look like and models in physics look like. Okay, so that's if you want the motivation behind what I do and my research program and so on. But let me tell you now what I have in the talk in particular, right? Like, so how are we going to use this probabilistic models to simulate quantum physics, right? So that's, if you want, the how and the contents of the talk. So first, we need a formulation of quantum theory that looks like probability. So I'm going to show you how to do that. And then we'll use the generative models, in particular recurrent neural nets and other models called transformer, to parameterize quantum states. And then I'm going to show you one example to motivate why this may be a good idea in the context of quantum state reconstruction. So which is basically when you have a quantum state in a lab, for instance, you measure it, and then you want to infer a possible quantum state that is compatible with the measurements. And finally, I'll show you a heuristic, another formulation of quantum computation in terms of probability distributions and generative models. So that's basically what I'm going to be telling you about. So what are quantum states, what are measurements, and probability distributions? I'm going to discuss this briefly and how to relate them. So how is quantum state traditionally described in quantum theory? So this is usually described through a density matrix that describes the statistical state of a system. And what we say is that everything we can possibly know about a quantum system is encoded in this density matrix, which is basically a positive semi-definite Hermitian operator of trace 1 acting on the Hilbert space, right, of the system. So basically, if you think about what is a density matrix, like at least for one qubit, you can see it as a vector inside this block sphere that I here plotted on the right. And that's, if you want, my density matrix, one of these vectors in this convex set of quantum states, the block sphere. And we've seen this in quantum theory and quantum mechanics courses. And this is the traditional description, but it turns out that there are other descriptions that are equally valid. So I'm going to explore one of them. So how to represent a quantum state with only probability. So this is maybe not surprising, but maybe a little bit unusual, right? Since we often hear that quantum states are represented by complex numbers and density matrices and so on, and that this is the magic behind quantum physics. But you can also represent quantum states with just probability, okay? And how to do it? One approach is through measurements, right? Like so, and measurements are described by a positive valued operator. So positive operator value measures, or POVMs. And what are these POVMs? They're just sets of operators M, and they're positive semi-definite. And basically, if you sum over a set of POVM elements, you get the identity. So that's going to be the main tool that I'm going to be using to represent these operators. And the other thing that is fundamental is this Born rule, which relates quantum theory to experiments, right? So in quantum theory, what you say is, okay, I'm going to take a quantum state that I prepared on the lab, and I'm going to apply measurement MA on the state. And if you measure this operator MA on the lab, then you will get outcome A with some probability PA. And this relation to the probability distribution is called Born rule, which basically Born invented, or like he just he used this intuition to propose that this was the case, and basically the probability of finding some outcome A is just this trace of rho times the measurement that you apply on the system. And this probability distribution is what I'm going to be using as a representation of the quantum state. However, you have to be a little bit careful. So you have to use measurement operators that are like that probe enough information about the quantum system for you to be able to say that all the information in your quantum state rho is also contained in your probability distribution P. Okay, so and that condition is called informational completeness. And what that means is that the measurement statistics of PA contains all the information about the quantum state. And so I'm going to be using informationally complete POVMs, basically measurement operators that probe enough information about the quantum state such that the information contained in this probability distribution is the same as the information contained in the density matrix. And if that's the case, then the relation between rho and PA can be inverted. So you can go from rho to P, as in Born rule, or from P to rho, as in the inverse of Born rule. And we're going to be taking single qubit measurements and make a tensor product out of them, which is basically like the motivation for taking those measurements as tensor products is because of this is the measurements that you have available in the quantum computers that people are capable of building as of right now. Okay. So that's the motivation, and so this is a little bit of a graphical notation and like this relation between the Born rule and the quantum state and the inverse. Okay, so here we have Born rule, which is basically telling you, okay, you have given you quantum state and a measurement that you apply in, say, an experiment, the probability of having an outcome A is given by this expression. And then if we have informational completeness, meaning that this operator probes a lot of information about the quantum state, then it means this relation can be inverted. And then basically the inverse is this thing here. It doesn't matter the details of the expression. The important thing is that rho can be specified in terms of this probability distribution. So basically what you do is you have this probability distribution and you attach some simple tensors and you get this density matrix. That's if you want, the most important message here, that you can represent quantum states with density matrices or probability distributions. Now, so quantum states live on this convex set, say for one qubit is a Bloch sphere, and now they're represented in terms of probability distribution, which live on a simplex. And probability, the points of the standard n simplex are this space of possible parameters or probabilities of categorical distributions with n+1 possible outcomes. And it turns out that this sphere maps into a kind of like a ellipsoidal region here that people in quantum Bayesian theory call Qplex, as kind of like a similar word to simplex, but a quantum one. So they add the word Q, as people do all the time in quantum physics, right? And so this is the set of distributions that we're going to be interested in, those corresponding to quantum states. Okay, so, and then the insight we had a while ago was, okay, so if this distribution specifies a quantum state, can we create models to approximate these distributions? And what we did was, okay, we're going to parameterize this distribution PA with a neural network that represents P, the distribution. And then we can invert and get this model for the density matrix. So we have a probabilistic model based on neural networks, and then we're going to have the model for the density matrix. And we're going to be using a particular family of models. They're called autoregressive models, such as the recurrent neural nets and the transformer, because they have some advantages. So one of them is you can sample these models exactly, so meaning that you every time you query the model, you get an exact sample in polynomial time, and they have a tractable density PA. So this is as opposed to, for instance, say restricted Boltzmann machines, where you, for like getting samples of the distribution, you have to do Markov chain Monte Carlo, and that's not even an exact sample, is only an approximate one, and where you don't have a tractable density, you only have a tractable and normalized distribution, which if you wanted to get the density, you would have to compute approximations to the partition function of the model, which are often very expensive, and they're only heuristics. So that's why we use those so-called autoregressive models, and they're very powerful and very useful for our purposes. So let me give you one example. So this is learning a quantum state from measurements. And let me explain a little bit of the setting here. So in this setting, what the idea is that we want to do quantum state tomography, or like we want to do reconstructions of an unknown quantum state that that is prepared in the lab, right? Like, so here we have examples with trapped ions on top. Then we have, I think, cold atoms in here, so where you can apply measurements and get, say, some statistics of the measurements that the system produces, and so on. And the idea is that quantum state tomography is very powerful, but it has some limitations because, for instance, the scalability of the traditional standard quantum state tomography is always a limiting factor. So it's exponential in the size of the system. And the idea is that we need to go beyond this standard quantum state tomography techniques because of the scalability of the quantum systems that we're able to prepare and control nowadays in the lab. So it goes beyond what you can analyze with standard tomography. But the idea is that standard tomography or neural network tomography goes like this. So you prepare an unknown quantum state in your lab, or like with your trapped ions or your cold atoms or with your superconducting qubits, and you apply a measurement that probes enough information about the quantum state. You repeat this on, and then you collect statistics of the measurements. And then you infer a reconstruction of the quantum state, say rho star. Okay, so that's the idea, and then you use this reconstruction to benchmark the preparation of your quantum device. Like, is your quantum device working as you was hoping to do? And this is especially useful in this like age of synthetic quantum devices that are growing really fast. So, for instance, probing, like here I have some examples of like very large quantum simulators. So one of them is probing the dynamics of quantum 51 qubits with I think this is called atom simulator. This is with 53 qubits. I think this is trapped ions. So this is observing some costally Staules transition with 1,800 qubits. Plus some more, like quantum chemistry with trapped ions and so on. So the need for for like benchmark tools to benchmark these quantum devices is growing fast, and so these techniques are kind of like aimed at those systems. So here I have some examples where what I did was to prepare ground states of local Hamiltonians and then simulate this measurement process on synthetically prepared quantum states. So, and here I have, like, for instance, ground state of the transversal model for 50 spins, which, I mean, you cannot deal with quantum state tomography, the traditional approach. And then I use this synthetically generated data to reconstruct the quantum state. And here I have in figure A and B examples of the reconstruction. So the synthetic state is this red line for the expectation value of some correlation function, sigma x, as a function of psi I. And green is the reconstructed state using a recurrent neural net based on a gated recurrent unit. And this is, which is one of the traditional neural network language models. And as you see, like match between the synthetic state and the reconstructed state. The correlation function is pretty good. And here you have like a two-body correlation function, sigma 1, sigma I as function of I, and the agreement is, again, very good. So panels C and D, we have a little bit of a better example in that this is a more challenging system. So it's a two-dimensional system, and it's the ground state of the Heisenberg model in two-dimensional triangular lattice. And these are correlation functions of both the synthetic state in panel C and the reconstructed state in panel D, and the agreement is, again, very good. So we were very happy, and we published some of these results in this paper in Nature Machine Intelligence last year. So that's just, if you want, an example of that exemplifies the power of our technique, or like the power of these models. So basically what we are saying here is that we can reconstruct complex states with a large number of spins, up to 50, and in this case, 64. So it's not a lot, but we went up to, I think, hundreds of spins, so 100, 120, and for different quantum states. So it seems to be working. It seems that if you want, the power of the technique is not going to be limited by the complexity. I mean, it is limited by the complexity of the quantum state, but at least for this ground states of local Hamiltonians, even for systems as complex as the Heisenberg model on the triangular lattice, is not a problem for this type of approaches. But we wanted to go beyond reconstructing quantum states, and we wanted to see if we could use this for actually simulating complicated quantum states. And so we asked the question, how about simulating quantum computations, right? And that's, if you want, what I wanted to tell you about today. And so let me tell you how we do this. So let me first tell you about circuits in our language. So we first, what is a quantum computation? So it's basically you take a very simple initial quantum state, and you apply a set of unitary gates, or one unitary matrix on the initial quantum state rho, and then rho u is the output of the quantum computation, and then you measure the quantum state. And then the hope is that doing this, you solve some hard computational problem. Okay, so this is, if you want, a summary of unitary evolution or quantum computation, and that's the traditional language we use, right? Like, so you take a density matrix and you unitarily evolve it, and you get some rotated density matrix rho u that solves some computational problem. It turns out that you can translate this process into probability using all these ideas about measurements that I was discussing before. And what you get is something very reasonable, very sensible, and is this thing here. So you start from, so you had an initial rho, so now you have an initial probability distribution P that represents, or that contains all the information about rho. And then what you do is you multiply that probability distribution understood as a high-dimensional vector times some matrix. And that gets you the time-evolved probability distribution PU that contains all the information about the rotated decimatrix rho u. And of course, this matrix that you apply to this probability distribution is related to the unitary that you applied on the matrix, and it has this relation, right? Like, so it's obviously depends on you and the measurement operators that you're using. It turns out that this relation here, this expression that relates the two probability distribution is like the evolution of almost classical probability distribution, except you're using this matrix P O A prime, and it turns out this matrix has been studied in the math literature a little bit, and they're called somewhat stochastic matrices or quasi-stochastic matrices. And they're not like stochastic matrices, but they have common things. For instance, in a stochastic matrix, when you sum over the columns, you get ones. And this is also true here, like for this probabilistic gates or the somewhat stochastic matrices. If you sum over the columns, you get one. But the difference with stochastic matrix is that the entries of this matrix can be positive or negative. Okay, so this is, if you want, the reformulation of unitary evolution in terms of probability distributions. You replace density matrices by probability distributions, and you replace unitary matrices by somewhat stochastic matrices. And everything else in quantum theory follows from this relation, like Schrödinger equation, measurements, quantum channels, Lindblad equations, and so on. So here is, like, for instance, how quantum dynamics for closed systems look like. So you go from this von Neumann equation for the density matrix, you go to this equation for a probability distribution. It's kind of like a differential equation for the probability distribution that you're trying to time evolve. And this has a solution that is in principle simple, and it's just basically in terms of this giant matrix A that is depending on depends on the Hamiltonian of the system. And this is basically the solution, which is basically multiplied by e to the minus iat times the initial distribution. So that's like an aside, but I think it's very neat. But let me go ahead and tell you about quantum circuits and quantum computations and how we simulated them. So the way we did it was we start with the way quantum computation goes is you start from a very simple product state with 0, 0, 0, 0, for instance. You apply a sequence of local unitary matrices or unitary gates that act on the initial quantum states sequentially. And then at the end, you apply a measurement on the resulting state. So this is represented here. And then what you do is you with this measurements, you basically that's the end of the computation. So the idea is, in general, this is what a quantum computation is. Sorry, just 1 second.
Papá.
Un minuto, Martín, por favor.
Papi, no, ¿cómo?
Me estoy hablando con la gente.
Papi, pero ¿cómo pone el volumen y cómo quita el volumen? ¿Cómo le pone la cara?
Martín, silencio, por favor. Sorry, I apologize about that. So that's what a general quantum computation is. So basically the quantum algorithm is just a set of unitary gates, and they are designed so that measuring the evolved quantum state at the end of the application of the gates results in the solution of a computational problem. And what the people do in quantum computing is basically you prepare this initial state, you apply this unitary gates, and then measure. And you can do the same with this language that we use. So the probability is the initial probability distribution P0, you apply this probabilistic gates, and then you get some probability distribution PU at the end. So how to simulate that? So in principle, you could try to simulate this using Monte Carlo, but it's very difficult because this probabilistic gates have positive and negative signs, which leads to the so-called sign problem, which we cannot avoid in this setting. So it makes the simulation using tools like Green's function Monte Carlo impractical. So how to do it then with probabilistic models or with generative models? So let me explain first the application of one gate. So you you take an initial distribution P of A prime, you multiply it by the so-called somewhat stochastic matrices O, and then the results into a probability distribution PU. So this cannot be done exactly because, as we said, P lives in a really high dimensional space. So can we do it approximately? And that's what we're trying to do here. So basically what we do is, we assume we know PA prime, and what we do is we introduce a model P theta that is going to try to approximate the time evolved or the unitarily rotated PU. And what we do is basically we compute divergence between the model p theta and the time evolved pu. And we do that through some sort of sampling. Basically, the distance or the divergence that we use is the KL divergence, which is this quantity here, which is, if you want, a statistical measure of distance between probability distribution. So it's this object here that it is such that if p theta is equal to pu, then this quantity is 0. Okay, and then we basically rewrite this quantity in terms of our model, and it turns out that if you use one of these tractable models, such as the transformer and then the recurrent net, you can compute efficiently this KL divergences, okay, and the gradients of this cost function or this statistical distance. And so what we do, so I don't want to go into too many details of the math, is we can approximate this distance between the probability distribution p theta and pu, and we can then minimize this, use this cross entropy or this KL divergence using samples from p or even samples from p theta, as we show in our paper. And this algorithm that this idea that I explain here are the simplest, if you want, incarnation of the algorithm that we've introduced. But there are more sophisticated versions of this and improvements. And I encourage you to take a look at our paper, which is this here. It was put on the archive in December. So that's the gist of it. And so if you want to do multiple gates, you basically repeat this process on and on, right? So you start with some probability distribution P0, you introduce a model for P1, which would be the exact P1, or if you want, as if you could multiply this matrix O times P0, you would get P1. But instead, we introduce a model P theta 1 that we try to get as close as possible to P1. And then what you do is we assume that the P theta 1 is close enough to P1, and we try to model P2 based on that model. And then we introduce a new model P theta 2 to try to match this time evolved P2, and so on. And you repeat and repeat. And at the end, you will have if you want, an approximate representation of the quantum state after all the gates have been applied. Unfortunately, errors will accumulate since this training is not performed exactly, so that's what makes the algorithm a heuristic. So we can try to minimize this KL divergence, and if we get it to exactly 0, then this algorithm becomes exact, but in practice we can't do that. So we do it approximately, and that's what makes the algorithm heuristic. And so let me show you a couple of examples. There are simple states. One is the G8Z state on n qubits, and the other one is the linear graph state. So the choice of the states is because they're simple and they're easy to simulate exactly for a large number of qubits, and so we use them to benchmark our technique, and so that's what we use as, if you want, as an example of our techniques. And also the other thing is they have a small number of gates, because the complexity of the calculation depends very much on the depth of the circuit, and so we wanted to use some quantum circuits that are not too deep. So here are examples of training these models for two very simple states. One is the Bell state, and the other one is a graph state. So A, B, C, D is the preparation of the Bell state, which is basically applying two gates, so the Halmar gate and this control X gate on this this product state 0, 0. And here I have the KL divergence between our models P theta I and the exact distributions Pi. And this is only for 2 qubits, so just to verify that everything is working well. And what you see is that this, like as a function of the training step, this KL divergence goes to 0 exponentially, at least at the beginning, and then it saturates. And the same is true when you apply the second gate, X, which you see here, initially goes exponentially fast and then it slows down. And as you see, when you apply the first gate, you get some like very, very good error, like errors in the KL divergence of like 10 to the minus 8. But when you apply the second one, since you're doing it on top of an approximate state, then your error accumulates a little bit more and your error is a little bit bigger. And the same is true for if you want this classical fidelity or the infidelity, so 1 minus the fidelity between the two distributions, it goes exponentially fast to 0 and then saturates, and the same is true when you apply the second gate and so on. So these are basically telling you that this technique is working and that we have somehow like a good handle over what we're trying to do. And this is the quantum fidelity. So as you train, it goes like to 0, right? Like the infidelity goes to 0. And the same is true at the second gate. This is another example. So figures E through H, they basically telling you the same, right? That when you apply one gate on this plus, which is basically preparing this graph state, that this infidelities go to 0. And that's the good news. Everything is working, and this is based on a transformer architecture that I have drawn here, and the details of this is in this archive paper here that I mentioned already. But then we wanted to see if we could go and explore larger systems, because we want to see if we can simulate big systems, right? And so we went up all the way up to 60 qubits. And here we measured the fidelity of the preparation of these two quantum states. So for the GHZ state and the graph state. And so what you see is that, yes, as the number of qubits increases, the fidelity or the classical fidelity of the calculation decreases. It's not too bad. It reaches 0.9. So it's maybe not the best, but the other thing we observed is that, for instance, for the GHZ state here in orange, so if we have a model with 32 hidden units, or which is, if you want, the memory capacity of the model or the power of the model or the expressive power of the model, if you increase it to sorry, I'm talking about the graph state here in orange. So versus the graph state with a smaller model here with 16 hidden units, when you see that there's an improvement of the results as you increase the power of the model, meaning that there's potential improvement by improving the potential, the expressive power of the model. So we see decent results. I mean, we can simulate systems as big as 60 qubits, and so we were happy about it. And that's it. I mean, that's the results that I have so far, and I think I'm running out of time in about 2 minutes. And so let me try to draw some conclusions. So I guess we started with the question from this 1981 paper. Can we simulate systems or quantum system probabilistically on a quantum computer? And the answer was no. But then we asked, can we reformulate this problem the same way Feynman proposed it in his 81 keynote, but in a variational way, and using, if you want, modern techniques from machine learning, like neural machine translation and neural networks. And so what we did was we came up with a reformulation of quantum theory such that asking that question is possible. And then what we did was show a heuristic using transformers and recurrent neural nets to that we demonstrate that we can use probability and probabilistic models to simulate quantum circuits. There are good aspects about this. So one is the optimization of the scale divergence is relatively easy. It works. But it requires some tricks, and sampling is tricky. Or sorry, no, the sampling is okay, but you need to you need some tricks to improve the variance on the estimator of the gradients that you use in the optimization and so on. So there's some improvements to be done, especially regarding the optimization of the models. There are some open scenarios where we could apply this, as for instance, simulating open quantum systems, real-time dynamics of both open and closed quantum systems, and everything is just using probability. So I think that's kind of like some set of open directions, and with that, I would like to conclude. Thanks, and I apologize for my son showing up.
Hold on. Thanks a lot, Juan. So this is a little bit an awkward moment because nobody's clapping, but this is sort of virtual clapping, and I think no need to apologize for your son. I think we've seen this as CNN and BBC, right? So I think we are perfectly okay with that. So I guess I just would like to open the floor to questions, and there is already another question here, but let me maybe ask one myself. That is kind of a more general one. Now, I mean, I personally not ultra familiar with this notion of interrogating quantum system through interrogating probability, right? And I just wonder, I mean, why we have to go through that? I mean, what is the main rationale to go that? Can we just do simulate, say, the dynamics directly at the level of density matrix?
Yeah, so that's an excellent question, and you can do it, right? Like there are approaches to simulating density matrices based on, say, neural networks and so on. And but I guess I don't know if you're familiar with this, but optimizing this complex neural nets it's tricky. Right. So and like for instance, when you try, like, we've done this too. Like for instance, when you're solving for frustrated problems and so on, this optimization becomes really hard. And most, if you go and see the simulations out there that use neural nets to parameterize quantum state, most of the time they use quantum states that are simple to optimize, meaning that they're coming out of stochastic Hamiltonians that require only wave functions that are positive, so that these models are very natural. Of course, there are examples where people have tried solving problems using directly neural nets that involve systems that are positive and negative, and whose wave functions are more complex, and this works in principle, and in practice for some systems it works well, but for some systems it just doesn't work. And I experienced this myself with my collaborators. We tackled this problem of optimizing neural nets for frustrated systems, and they work really well, but they don't beat the state of the art, say, for instance, based on variational Monte Carlo, like the traditional variational Monte Carlo, like that I studied, for instance, during my PhD with Federico Becca and so on. So one motivation for going through the probability setting is that you don't have this issue of having to deal with complex numbers. So everything is positive, and the optimization problem is just much easier. So that's one motivation. And the other motivation was because these distributions are directly what you can measure on a quantum computer.
Right.
Yeah. So I have those two answers.
Yeah. So I guess yes. I guess so. If you work through the probability, essentially, you're already working on the output of the quantum hardware, if you like. Right. That's essentially.
Yeah, exactly. That's exactly what we're trying to simulate. We're not trying to go through the density matrix. We're going to do the simulations directly on the outcome of the quantum computer. That's perfect. Yeah.
Okay. All right. So then let me read the question. It's from Michael Moscalets, and he's asking, okay, thanks for the nice talk. How to model negative probability? And the second question is, what is their counterpart in your approach?
So we wanted to avoid this negative probabilities. So if you wanted to go through negative probabilities, then you can use some other representation. Like, for instance, you could use this Wigner function representation, and then you get this negative probabilities, and then you can represent this with a model by adding, for instance, a second layer out the outcome of this like recurrent neural nets or this transformers, such that you can encode a phase, and then you would be able to represent negative probability. But that's exactly what we wanted to avoid, so we didn't try to simulate those.
Yeah. Okay. Now. Okay, so let's see if there are other questions. I don't see any. I mean, maybe I'll have another question myself. I mean, how does exactly the training of this nets work? So you simulate a kind of unitary evolution, and then coming from a number of initial conditions, and then you train the network on that, or I mean, how does it work exactly?
Yeah, okay, so I went too fast through that, so I apologize. So what we do is, here, right, like, so you have an initial distribution, like let's say P0 at the beginning of the circuit. So that distribution is very easy to simulate exactly, okay? And so what we do is, there are different approaches, but one of them is the one that I wrote here, is we compute, given samples of the initial distribution P0, you can compute the KL divergence between this distribution PU and the P theta, your model, okay? So we don't need data if you want. The data is self-generated out of samples from the distribution P0. Mm-hmm. And so basically you can see it here. So this is, if you want, the most important part of the equation that we have is, and we have here samples from the distribution, the original distribution P, that we can do exactly because P0 is very easy to compute, right? Like as our initial state, and so we get a big bunch of samples from them, and then we have this operator O A prime that is local. So this second sum is efficient,
yes, and
the logarithm of P theta is the model. So, and one of the premises of our approach that we had access to the amplitude P theta of the model efficiently. So this estimator is efficient as long as you can get samples from P. And that's what we do, right? Like, so basically we take samples from the previous distribution that you want to approximate, and then you use those samples to compute this quantity and the gradients of the quantity. And then you follow the gradient descent.
So, say, strictly speaking, you don't really train on, say, simulated or real trajectory, if you like.
That's right. Yeah, we don't, and we didn't want to do that because otherwise you would be introducing the problem back again, right? Like that, right. You're trying to simulate a system, and you're using probability distribution, but at the same time you would be using a different simulation of the same system to train this. But we don't want that, right? Like we want to be a simulation that is capable, in principle, of doing everything on its own.
Right. Okay, so let's see. Okay, so there's a question from Luke Koopmans, who I believe you know. Yeah. He's asking, how is the error scaling with the number of gates in the quantum circuit? And then, well, okay, maybe this question, then there is a second one as well.
Yeah, so that's a much difficult question to answer because everything is heuristic, so we don't know. So what we see, it's roughly, I mean, the error that we make is not decreasing exponentially, or more like a linear. But this is based on this figure, and I mean, it's hard to give an answer given that the data is not perfectly following a trend. So it's not following a very clear trend. So and since everything is heuristic, we don't have an answer for that question. But it's a very good question.
And the second question Luke is asking is whether you did consider also imperfect gates.
No, but it's a good question. But the answer is no. But it is possible because we can. So the interesting thing is the same setting here. So this OA, so this exact same equation works for both unitary matrices, but also general quantum channels. So in principle, you can simulate noisy gates using the exact same approach. And this is something I thought at some point about doing, because it may actually, I mean, using noise in the gates that you apply may help with the accuracy of the simulation. So it may be easier to simulate, say, noisy, imperfect gates in this setting versus doing what we're doing, which is simulating unitary gates. So that's a good, if you want, that's a good direction if you want. Yeah.
Okay, so I don't see any more questions coming, and I mean we got essentially the end of the hour, so maybe I'll close here the discussion, and I would like to thank Juan again and all of you for listening, and I guess we'll see you again in a week time. Thanks a million.
Yes, thank you so much, and have a good day or